Good morning, and thank you for joining us here. Here we are, it's the Future Panther Academy, and my name is Bonnie Fugiasco. I serve as the Special Events Manager for the Alumni Association at the University of Wisconsin-Milwaukee. So welcome back to all of you who have been with us in the past, and welcome and hello to all of our new viewers today who are joining us for the first time. We are presenting the fourth program in our new 9-week Friday morning series called Stars Have Stories. We are presenting this program in partnership with the UWM Planetarium, and that's where our program host, Dr. Jean Creighton, who's an astronomer, has been the director since 2007. Today's episode is called How Far Away Are Stars? And if you're watching today's presentation live right now on YouTube, you can send us questions for Dr. Jean using a little chat box just to the right of your video as you're watching us today. At the end of the program, Dr. Jean will answer as many questions as we can get to, okay? And just a reminder, if you've missed any of our previous programs or you're interested in finding out what's coming up next, you can find links to everything on our website. So take a look and you can watch anything anytime on demand. So please feel free to do so. All right, everybody, let's get settled in. Dr. Jean is getting ready to present this week's episode called How Far Away Are Stars?
Thank you, Bonnie. I'm really excited to talk to you about something that people ask me all the time. How do we know how far stars are? Because really, if you look at a picture of the sky, it's not possible to look at this and say, that star is nearby, that star is far. And sometimes even when you think you know, you might be wrong, because it could be that you have a star that's super, super bright, that looks brighter than a star that's nearby and just faint. So we're going to talk today about two different ways we do that. First, for stars that are kind of nearby and stars that are really far away. We're going to start with the nearby stars first. And I'd like you to do this an experiment. We're going to imagine that we would like to figure out how far this wonderful boat is, this sailboat. And the sea is kind of like sky. It's hard to gauge how far is that boat from us. What I'd like you to do is take your thumb about, 4 fingers or so from your nose and try and put your thumb right in front of block the boat and close one of your eyes. Okay, got that? Good. Now I'd like you to close the one that's open and open the other eye. I'm hoping that you had a revelation, like, oh, my thumb moved. The ship is not covered, the boat is not covered, that my thumb seems to be out in space. This is called parallax. Why do we see this? Well, your thumb is so close to your nose that if you're looking at the thumb with respect to the boat from this side, it's different. The perspective you have is different than if you're looking from the other eye. Now, I'd like you to put your thumb at arm length, right up to the boat. Do the same trick. Close one eye, and your thumb should be smack on the boat. And then I'd like you to change your eye. Did it change as much as it did before or a little less? I'm hoping you'll say a little less. The point now is that because your thumb is much farther from your face, whether you look at it from this side or this side doesn't actually matter quite as much. So that shift we call parallax becomes smaller for more distant objects, okay? So we use that idea. In fact, this whole idea of how do I measure the distance to something far away, be it a boat or a tree or something, gave birth to geometry. This idea is now more than 2,000 years old, where people realized we need tools to measure how far things are, and that's what we did. We used geometry, which literally in Greek means geometria, means measuring the earth. In this case, we have a tree at a distance, and let's just say maybe there's a river between us and the tree, and we can't tape measure and measure like we normally would the distance to the tree, but we have two locations, location A and location B, and I can measure angles, right? People have had compasses and protractors for a long time. So person A measures the angle between the tree and position B. That's an easy measurement. And either another person or the same person just moves to position B, measures the angle between A and the tree. And let's say they're willing to take a tape measure and measure the distance between A and B. That's all you need. That's the beauty of geometry. If I have two angles and a distance between them, I can figure out every distance of this triangle and every angle. That's the beauty of it. So we are able, and this is the kind of trick we used to measure some of the very closest stars. Now, those people are like surveyors, and maybe you've noticed surveyors in your neighborhood, people who use, these are machines that help us measure angles. And the question is, how can I change my perspective? How far can I go to see a star from a different place? You might say, oh, we'd pack our bags and go thousands of miles away, and that would change your perspective, but not all that much compared to how far stars are. That's not going to make a difference. But this is what's going to make a difference. Wait for half a year. If you just stay put for half a year, the Earth's orbit is so large, in 6 months, you're going to be 300 million miles away from where you are now. So if you have a telescope on Earth, that's what you would do. You would wait for that time and you would measure that angle from those different positions. Now, our instruments on Earth are limited because we have an atmosphere. If we wanted to do better and measure angles that are really, really small, so that we can see really, really far, we use Yeah. This is a picture of Yeah. This is an instrument that is mapping 1 billion stars. I said 1 billion, that's 1 with 9 zeros of stars in our galaxy. And it has an exquisite accuracy with which it can do that. Let's see an example of data that comes from Yeah. I'd like you to notice the star in the middle. We have a red circle around it on the left side. And I'd like you to notice its relative distance to some of the stars nearby. There are 2 really, really bright ones on the right-hand side and 2 kind of fainter stars that are straddling it on either side. Now look at the right image. You see the star has moved with respect to those background stars, and that would be parallax. So you notice that now it seems to be almost halfway between the 2 stars, the fainter stars above it. I don't know if you can see that, but I'm hoping you can, that there has been a relative shift. We call that parallax. And based on that small change of angle using our geometry, we can figure out how far those stars go. How far those stars are. Now, to impress upon you how fantastically accurate this machine is, I'd like you to imagine that Bert is sitting on a chair and he's reading his newspaper, and Ernie is kind of leaning over Bert's shoulder so that he can read the newspaper too without bothering Bert too much. Ernie would be able to see a period in the newspaper if he packed his bags and went all the way to Beijing, China. I'd like you to think about that this machine, if Bert was sitting in a chair in Milwaukee, Ernie would be able to read a period in the newspaper with Yeah if he stood in Beijing, China. That is how magnificent, high the resolution is. The quality of the image would be so high that you could do that. These are extraordinary machines that give us extraordinary data to understand the universe more. So this wraps up things that are relatively close, because frankly, even stars in our own galaxy are relatively speaking nearby. What if I wanted to look at stars or even galaxies that were much, much farther away? So for this, we use a different idea, and I'd like to celebrate the image that you're seeing here. This is an image of a galaxy in the Virgo constellation, and we've named the supernova there. There is a star that has gone kablooey. We've talked about this before. A supernova here is so, for a few weeks, is going to be so bright. It will outshine the entire galaxy. So the 200 billion stars in that galaxy are going to be dimmer than this supernova at its peak. The other idea here is that supernovas, when they reach that peak, are like what we call standard candles. They're always as luminous. They always get to the same brightness. So you can imagine a certain kind of supernova is like a candle. It's the same kind of candle. If we had them side by side, they would be exactly the same brightness. And if they looked different, it would be because one of them is close and the other one is far. But we would know that if they were at the same distance, they would be exactly the same. They would appear to us exactly the same brightness. Now, what's interesting about how bright a star looks like, and we're going to pretend here that our candles stand in for stars. If you double the distance to a star, even if they were the same, like these two candles, they were the same brightness, same luminosity, they make the same amount of light. But if I double the distance to one of them, then the brightness, it appears quarters. So it's a very strong connection to distance. If I double the distance, the object appears a quarter bright, which tells me that if I knew that the two things were equally bright and one looks a quarter the brightness of the other, that tells me, I understand. That one is twice as far. So that logic helps us understand how far distant objects are. I'd like to give you an example in the night sky. This is something I set up in my living room. These are two candles, and I would like you to think about, do they look equally bright to you or not? And if not, which of these two stars looks brighter? I'll have you think about that for a sec. Which of these stars looks brighter? I would say it's hard to tell. You might say, maybe they're kind of similar. You might say, maybe the left, just because it looks bigger. And I just want to put a note here. These candles are really close to us, right? And therefore, you'll be able to see, the one candle's flame looks bigger than the other. But of course, for real stars, we can't do that. All stars are just little dots in the sky. But I'm making a case here that these two stars are pretty equal in brightness. It would be very hard to say with confidence one is brighter than the other for sure. Let's see what this setup looks like from above. This is how I set this up in my living room. And I tried to use every trick I could to hide the fact that the really brighter star, that was a much brighter candle, was much farther away. And that was the one on the right. That candle was significantly brighter than the one on the left. But they were at different distances. And I just wanted to say how hard it is to tell. So the bright star happens to be far, and that's in fact what's happening in the night sky for real. When you see a star and you think, whoa, that star is really bright, it's not because it's close. Most of the stars that look super bright are indeed very luminous, and you can see them even though they're far because they make so much light themselves. This technique has allowed us to see very distant objects. this is a picture of what turns out to be a very distant object. This is called a quasar. And when we first discovered quasars, they had some weird features. We had no idea what they were. And I'm hoping that you notice in this image, doesn't look so special, right? It's like, it's an object that's not particularly bright compared to other things in the picture. And what we realized was this object is 13 billion light years away. That means it is 13 with 9 zeros following. It is extremely far. And when people realize, wait a second, if it's that far and we can still see it, it must make a tremendous amount of energy. And when they did the math, they realized this thing is 1,000 trillion times brighter than the sun. Whoa. How do you even do that? How do you even make something produce that much energy? And that's what made quasars super cool. They are very young galaxies that have an active black hole in the center that is busy eating up as much of the material around it as it can, thereby producing an extraordinary amount of energy in the form of gamma rays and other things. This is obviously an artist's impression. We can't see quasars that look quite as detailed as this, but it shows you the parent galaxy. It shows you the black hole in the center, which of course is silly because we can't see black holes, but anyway, fine. And material gets shot out along the rotational axis of the galaxy and produces this very bright light that if we happen to be in the path of that beam, we get to see quasars. So finding the distance to an object opens our eyes to beautiful distant objects and tells us about the history of the universe. And I imagine now that I have made your brain go, and I'm looking forward to your questions.
I love that picture of the quasar, Dr. Jean. That was cool. So our first question comes from McKenna, and McKenna wants to know, if I stood outside in Milwaukee, which star or constellation is closest to me?
Great question. I'll clarify first about the constellation part and then the star part. Constellations are groupings of stars that happen to be in the same line of sight. So you could have one star here and one star, I don't know if you can see this, I hope you can, one star here, one star there, and to us, they all look like they're in the same constellation. So they aren't necessarily at the same distance with us. So it's hard to answer that question because different stars in the same constellation might be at very different distances. But I can tell you that the closest star that we can see in Milwaukee would be something like Proxima Centauri, as it turns out, is too faint. You would need definitely a telescope to see that. So your best bet would be something like 61 Cygni. This is a star that's relatively bright and only 11 light years away. And you will be able to see the stars in Cygnus before the sun, later in the evening, frankly, probably after you go to bed and before you wake up. But if you wait for another month, you'll be able to see many beautiful bright stars in Cygnus. Great question, McKenna.
Thank you. Yes. All right, our next question is from Jack, and Jack wants to know, do stars get closer to the Earth or stay about the same distance away?
That's a great question, Jack. For all practical purposes, stars are going to be basically at the same distance to you. The changes that are going to be made are going to be very small compared to how far they are. And therefore, you'll only be able to notice stars moving very small amounts in the sky with a super powerful telescope, and only for the stars that are really close to us. So the short answer is yes, stars do move in the sky, but to be able to notice it is hard. You can only do it for really nearby stars. Great question.
All right. And our next question is from Allison. And Allison asks, is the sun the oldest star in the sky?
Wow, Allison, nice question. We can find how old different stars are. The sun isn't all that old. There are stars in the sky that are going to be younger than the sun, but they're going to be stars. So to give you an idea, the sun is, let's say, about 5 billion years old. That's 5 with 9 zeros after that. They're going to be stars you can see in the sky that are only 10 million. That's 10 with 6 zeros. And there can be stars in Hercules that are almost 13 billion years old. That's, again, 13 with 9 zeros. So the sun is certainly not the oldest star you can see in the sky, but it's getting up there. It's certainly a middle-aged star. There are going to be plenty of stars that are younger than that. Great question, Allison.
Okay, and here comes a question from Lila. She wants to know, how far is the furthest star we can see at night in Milwaukee?
You know, if you have a telescope, the answer would be different. But if you had a really powerful telescope, you know, the most distant star is going to be many thousand, 13, 14,000 light years away in even our own galaxy. But if you were to look just without any help, your brightest, the most distant star you can see will be something like Rigel. And that's going to be, you know, about 800 or 900 light years away. That's in Orion. Great question.
Okay. And let's see, we have a question from Ben. And Ben wants to know, what was the first star's distance we could measure?
The first star's distance. Using Parallax, we were able to measure Barnard's star, one of the very first ones. This would have been first measured in the early 1830s. It would have been first measured. So this was the first time we could actually measure that shift with respect to background stars because our telescopes were good enough. So that's a triumph of human invention. That's almost 200 years ago now, right? That's great. And is that our last question? Okay, so let me kind of recap here, and we'll look ahead for next week's program. So today we talked about a tricky question because so many properties of stars depend on how far they are. And we said, we have two ways of knowing how far stars are. One is by looking at parallax. That is, how does the apparent position of a star change with respect to background stars? And we did an experiment that shows us the closer the star is, the more it seems to shift, and the farther it is, the harder it is, which makes it, of course, eventually impractical to use parallax, which is why we need the other way of thinking about it. If you could imagine that you knew two stars make the same amount of light, and given the idea that if I double the distance between the two stars, I'm actually going to see a difference of a quarter. So the brightness is going to drop to a quarter of the brightness of the star near me, that tells me, oh, these two stars look different because they are at different distances. And we use that to great effect to look at even far, far away galaxies. And this has given us insight in some of the beautiful energetics, what powers some of these bright things that we can see across the entire universe, like quasars. And I have prepared, you're going to get that, I think, later on today. I have prepared an activity that you can actually experience that with more familiar objects. You can find in relative terms how far, say, is a star like the North Star, how far is it compared to a galaxy, the Andromeda galaxy, and how far is it compared to one of those really distant quasars. So I hope that you enjoy that activity, maybe sometime today or maybe later. And next time we're going to talk about how fast stars move, how do we know, and that will get us back to that interesting subject of understanding the big from understanding the small. And I look forward to having that conversation with you next week. Thanks very much for listening and for your questions.
Okay, we're out. Great job.
Great.
Yay!
Yay. All right.
Good.
So